in the actual equation that gets used here, yes, c is the limit to growth. Okay, and it's this horizontal asymptote that we're leveling off to. That's c. Okay, so this y value up here, that's c. So we always start at 0. There's two horizontal asymptotes for every logistic. There's the x-axis, which is y equals 0, and then there's also y equals c. Okay, so maybe we'll jot that down too. Okay, and then there's always this mistake that students make with this too, where I ask them, okay, here's a logistic function, tell me what the initial value is. And they go and they find the a in there, just like the regular exponentials, and say, oh, there it is, I found my a. That's the initial, just like with exponentials. And it ain't the case this time. Plug in a 0. If I plug in a 0 right here, I get b to the 0, which is 1, so it's gone. But then what's left over? There's still 1 plus a down there, right? And don't forget about the c. That's still there too, right? So the initial value of a logistic is actually c over 1 plus a. So the initial value, or y-intercept technically, is c over 1 plus a. And really, just plug in a 0 if you're going for that. That's all you're doing, is just plug in a 0. So, all right. So let's see if we can analyze a logistic function here. Okay, so how about f of x equals 2 over 1 plus 4 times 2 to the x? So what's the initial value? And what's the limit to growth? Let's start with that because we've already talked about both those two things. And I bet both of those two you guys can do in your head here real quick. Okay, so what is the initial value here? 2 over 5, right? Because this would just be 1 plus 4 after this goes away. So 2 over 5. And what's the limit to growth? 2. Good. All right. Let's see if we can find some other stuff here. Now remember, this is the graph of it. If every logistic kind of has that shape. What are my x-intercepts? None. Good. It never crosses the x-axis. We already did the y-intercept. How about horizontal asymptotes? So for this particular function, what would be its horizontal asymptotes? Yeah, y equals 0, y equals 2, and then, since I got a little room here, what would be its vertical asymptotes? Yeah.
Wait, how do you know the x-intercepts?
How do I know there are none?
Yeah.
Because every logistic looks like this, and there's always an asymptote down here, so it never actually comes down and crosses it. So it's always stuck above, kind of like that one. So vertical asymptote, there's none. Yeah, every logistic that's the case. There are none. Okay, and it's all because of that horizontal asymptote of y equals 0. It's never going to get down past that. It just kind of comes down and approaches it. So you'll never have an x-intercept. You'll never have any vertical asymptotes, anything like that. Even though it is a fraction, okay, getting this denominator to come out to 0 is not going to work in its basic form like this. So you're stuck. So good. All right, so can you go the other way with it then? If I give you some information about a population, can we make a logistic function? And if we can do that, then I'm going to be done. So let's say we got a wolf population. Begins with 20 wolves in a preserve. The preserve can hold a maximum of 200 wolves. And after 1 year, there are 40 wolves. So write a logistic equation to model the population as a function of time in years. Okay, I'll give you a second to write all that down. So there's some information in there that hopefully you're starting to kind of connect with what we talked about with how these logistic functions get put together. And that's going to help us get to an answer here. And I'll go ahead and copy down your basic logistic equation here. All right, so take a look at that paragraph of information there. I already know one of my A, B, or C's. Which one do I know and how much is it? C is how much? Right. It's a good place to start. We know C is 200. Okay. What other information did I tell you that might be kind of helpful here to get started? Yeah. All right, so that initial value we said was 20, right? 20 wolves there to begin with. So C over 1 plus A should equal 20. Can I put those two pieces of information together somehow? Figure something else out? What can I find now? A, right? So we know the C, so just plug that right in. 200 over 1 plus A equals 20. Okay, so it's going to take a little bit of work to solve that, but I think we can do it. How am I going to solve that for A? It would be a logical first step here. Okay, multiply that denominator up out of there. 200 equals, and I'll distribute 20 plus 20A. Okay, so then what? Subtract 20. So 180 equals 20A. So if I divide, what's A? 9. Okay, so I got C. Just got to find B now, right? So let's write down what we've got so far into our equation here. So f of x equals 200 divided by 1 plus 9 times b to the x. How am I going to find b? Plug in 40 and 1. What goes where? What's the x? What's the y?
Y equals 40 and 4.
Yeah, the y is 40. Okay, that's the f of x, or the y, is the population, right? How many? And the x in this case is time, because we said it has to be a function of time, so x is serving as time here. So yeah, let's do that. We'll plug in and then solve for b. So 40 equals 200. 1 plus 9 times b to the first, b to the first power there. So we've got 40 equals 200 over 1 plus 9b. So we're kind of in a similar situation as with the a thing there. I got to solve this for b, but we can kind of approach it the same way, right? I can just multiply this denominator up over to the 40. So we'll have 40 plus 360b equals 200. Subtract the 40. So 360b equals 160. And then what is 160 divided by 360? 0.4 repeating. All right, so we'll just say 0.44. All right, so this thing all put together then is going to be 200 over 1 plus 9 times 0.44 to the x. Okay, so yeah, just chop that off a little bit, but that works. So that should model our wolf population in the preserve here. So given a certain time, plug it in, I can figure out what the population is going to be. So, okay, homework. Let you guys get started on that then.